There we go. Okay. All right, so this example. Consider the radio factory from the previous example. So we started with an example of it costs them $7 per radio, and they have $24,000 that they have to pay before they even make any radios. So this was our cost function that we had from that previous example. So say we're using this same idea, and now we know that they sell each radio for $15. We want to define the revenue and profit functions. We technically did that on Wednesday, but again, I'm just going to go through it super quickly again, just to recap. So remember that revenue is equal to price times quantity, which is the big piece that you need to remember for that. So since our price that they're selling them for here is 15, our revenue function was 15Q. And then our profit function, well, profit is always calculated as revenue minus cost. So we found that by taking the revenue function minus the cost function. Always put the cost function in parentheses. I'm going through this somewhat quickly because, again, technically already did this piece of it, but always stop me if you need me to. So we're going to distribute that negative to both pieces. So 15Q minus 7Q is going to get us 8Q, and then we'll have minus 24,000. So that's as far as we got on Wednesday, so we need to do the rest of it. But just to remind you where all of that came from. So now we want to define the break-even point for part 2 of this. So again, now we have two options. We can either set profit equal to 0 or revenue equal to cost, whichever one floats your boat. Since we have the profit function here, let's just go ahead and set that equal to 0. But just to remind us, I'll kind of put off to the side that if you had done this, it will also work. So if we solve that, we're going to add the 24,000 over to the other side. Divide both sides by 8. You get Q equals 3,000. And now again, reminder, let me scroll back up and it'll go back down in a second. The break-even point is made up of two different things, the break-even quantity and the break-even price. So we just found the break-even quantity, and now I want to find the break-even price. So I'm going to take that quantity I just found and plug it into either revenue or cost, not profit. Because again, technically, if you plug it into profit, you're going to get 0. And that's not what we're trying to look at here. What we're trying to say is, how much is it going to cost me? And therefore, how much revenue do I have to make before profit is 0? So we technically want the non-zero price here when you're talking about break-even price. So you get to choose whether you want to put it into revenue or cost. I always put it into revenue because it's usually the easier function. Actually, I think we got through part 2 yesterday. You know what I mean by yesterday. Maybe we didn't. Maybe. Well, anyway, we're doing it right now anyway. So you get 45,000. Once my zeros stop lagging, there we go. 45,000 from that. So that means that our break-even quantity is 3,000 items and our break-even price is $45,000. So now we want to do parts 3 and 4. So let me scroll back up so we can read them. So we're going to sketch the revenue and cost functions and label the break-even point. And then we're going to sketch the profit function and label the break-even point. So we've got two different types of sketches going on. And I've mentioned this before, but when I say sketch, I mean they don't have to be really that pretty. They just have to get the point across. So in part 3, we wanted the cost and revenue functions. So I'm looking at these two functions right over here. So I've got 7Q plus 24,000 and 15Q. So let me go ahead and I'm going to do the cost in teal. So 24,000, well, that gets us our y-intercept, so we're going to be, decently high up on the y-axis. And then we're going to have a slope of 7, which is, not really that steep. So we're going to have a pretty not steep line. And that's going to be our cost function. And then our revenue function is 15Q. So that means that that's going to start at the origin at 0 because it's got a y-intercept of 0. It's It's got a slope of 15, which still in comparison to 24,000 is small, but it's a steeper slope than 7. So we just need to make sure that this line is steeper than the revenue. Than the cost. Again,
wait, I'm sorry.
Yep.
I have a question. How did you get to the position of the first line?
Yeah, so I'm working with this equation 7q plus 24,000. So remember that the 24,000, so this is in a y equals mx plus b format. And so this 24,000 is giving me my y-intercept. And this 7 is giving me my slope. So since I'm just doing a sketch and I'm not trying to make this super pretty, 24,000 is just giving me my y-intercept, which would, be pretty decently up on the y-axis. I'm not going to make it perfect. I'm not going to sketch it out completely, but it's just, high up there somehow. And then 7q, so that's telling me that I have a slope of 7. Well, compared to 24,000, 7 is a very small number. So that means I have a very small slope, which means my line is not steep. My line is, kind of straight, just kind of barely moving up as I move from left to right. So that's why I drew a very, is there a word for not steep besides not steep? A very not steep line that way. Did that make any more sense?
Flatter.
Yeah.
Flatter. That's a good word. Flat.
Thank you.
All right. Gradual. That's a decent one too. All right, so those are our two functions. Again, I'm just sketching these, so they're not perfect. They're not exactly how they would look, but they get the point across. And we really, the main thing we need to care about here is the fact that revenue has to be steeper than cost. That's the big piece here, is you want to get the y-intercepts, in a decently correct spot, and the slopes, if 7 is, flatter than 15, then it needs to be a flatter line than the revenue. So where's our break-even point on here? Well, since it's when revenue equals cost, that's going to be where they intersect. So here's our break-even point. And then we're essentially asked to do the same thing, but with profit. So, well, now I've got too many things floating around. I'm going to erase this piece that I just wrote. And I will leave the teal to remind us that that was that. But now let me pull out, where is our profit function? Let's do green. Profit function's over here. So we have 8q minus 24,000. So our y-intercept here is going to be the negative 24,000. So that's going to be somewhere, decently below the x-axis. Now here I have a slope of 8, which yes, is not very steep, but it's also the only thing I'm drawing. Like this is the only graph I have to draw, so I can kind of draw it however the heck I want because I've got nothing else to compare it to. And since it's a sketch, we can just kind of go with it. Because the main thing here is we just want to demonstrate where the break-even point would show up here. And that would be, well, when profit is 0, so when it crosses the x-axis. All right. Questions on that example at all? All right. Okay. Just a note that kind of gets lost down here a little bit. So we talked about marginal cost on Wednesday. And remember, the marginal cost was said to be the cost of making the next item. So, if yarn costs you $2 per each blanket that you make, then the marginal cost would be 2. The marginal cost in the example that we just did was 7, because each radio cost them $7. We can also talk about marginal revenue and marginal profit as well. It's not usually used as commonly, that's not a word. It's not used as often as marginal cost, but we still technically can talk about marginal revenue and marginal profit. And just like with marginal cost, if it's a linear function, those marginal revenues and marginal profits are going to be the slopes. So like in this case up here, the marginal revenue is 15 because that's the slope of the revenue function. And the marginal profit would be 8 because that's the slope of the profit function. So marginal isn't just a word that's used for cost, it can be used for revenue and profit also. All right, now let's jump to a slightly different idea. So we have the supply curve for a given item relates the quantity of the item that manufacturers are willing to make per unit time to the price P for which the item is sold. And I'm going to try to explain that in a bit more generic terms in a second. And then the demand curve relates the quantity Q of an item demanded by consumers per unit time to the price P of an item. So in that word verbiage, it might not make a lot of sense. So let me try to explain it with a bit more context. So say we're talking about that radio example, and I run this radio factory, and I've decided that I don't feel like making the radios myself anymore. I want to make somebody else do it for me. So I go over to some manufacturing company and I say, hey, I want to sell these radios for $15. Will you make them for me? And they're like, if you're going to sell them for $15, we'll make you 20,000 radios. And I'm like, cool. I've changed my mind. I want to sell them for $10,000. And they're like, I'm sorry, nope, got my numbers mixed up. I want to sell them for $10 a piece. I just want to sell them for $10. And they look at me and they go, well, that's less worth my time. I'm only going to make you 10,000 radios. So essentially, I tell them what price I want to sell them at, and they tell me how many they're willing to make me if I'm going to sell them for that much. Whereas the demand curve is essentially I go out to, the people and I say, hey guys, I'm going to be selling radios for $15. And they're like, cool, we're going to buy, 15,000 radios if you sell them for $15. And I'm like, all right, well, what if I sell them for $10? And then they're like, cool, $10 radios, we'll buy 25,000. So the demand curve is essentially, depending on the price of the item, how many are people going to want? So that's supply and demand. How many supply, how much is the manufacturer going to give you for the price of the item that you're selling it for? And the demand, how many people are going to want that thing based off of the price that you're selling it for. So looking at these two little graphs down here, given the following supply and demand curves, what do P naught, P sub 1, and Q sub 1 represent? So we have no numbers. We just have generic situations here. The other thing with supply and demand curves, it's kind of 50-50 as to whether or not quantity is going to be the X or quantity is going to be the Y, and it's vice versa. So make sure you're really focusing on which one's which on which axis, because it can change. It's not really set to be one over the other. But anyway, so in this case, we have our quantity being our X's and our prices being our Y's. So we have P naught right here. And I don't know what the actual value is, but I do know that that's the vertical intercept. So I do know that at this value, Q is going to be 0, because that's the only way that it would be in that position. So essentially what this is going to represent to me, and so this is the demand equation. Sorry, this is the supply equation. So this is when I'm talking to the manufacturers. So this is essentially going to tell me this is the price for which manufacturers are not willing to make any products. Radio example, I walk up to the manufacturer and I say, hey, I'm going to sell these radios for $30. And they're like, heh, not worth my time. Get out of my face. And I'm like, okay, sorry. So that's essentially, you walk up to them, you tell them a price you're going to sell it for. That was actually probably backwards. It was probably should have been a much lower number, but I got the point across. You give them a number, they say no. Whereas if I go over to my demand equation, well, let's look at P sub 1 first. So again, this is a vertical intercept, so this is still telling me that Q is 0 here, so the quantity that's being sold is 0. But now we're talking about demand, so in context, that would mean that this is the price, this is telling me the price, for which consumers will buy no products. I go out to the people and I say, hey, I'm going to sell radios for $100, and they laugh in my face and walk away from me. That would be that number, a number that's too high and no one wants to buy my product for that much money. Whereas with this Q sub 1, that's kind of gotten lost now in my words. This Q sub 1 is, of course, it's still an intercept, but now this is letting us know that P is 0. So the price is 0. So essentially these things are free. Now this one you might not think it makes sense, but it does if you really think about it. This is essentially the quantity that's demanded. I'm using demanded here because saying that it's sold for $0 makes me feel weird, so I'm going to say quantity demanded when the product is free. So, I could say, hey, I'm just giving away radios, and, a lot of people might be like, woohoo, free radio, even if they don't really need it. Whereas some people are just going to be like, nah, I don't really want a radio. So it does make sense to have kind of a set quantity for the number of people who are going to want that product, even if it's free. So that's that one. Any questions on that example? Alrighty. All right. This next one is a slightly common kind of setup. I think it's also common for future sections, but I might be lying about that. I don't remember. But anyway, it's a kind of common setup that we work with. So we have a movie theater sells 50 tickets a week at the price of $10 per ticket and sells, thing in the way, 75 tickets when the price is $8 per ticket. Find the demand function, assuming it's linear, as a function of price. Find the revenue function for the theater. So a couple things there. First thing we have to find is the demand function. So demand function as a function of price. So that's telling us kind of the order that we're going to treat our variables in. Now, demand and supply are both quantities. It's the quantity demanded and the quantity supplied. So while technically you can use D and S if you wish, it's a bit more usual to still use Q for quantity, especially because with this second piece of this question, find the revenue function for the theater, you might not realize right away what to do with the demand function if you don't have Q. So when we write demand and supply functions, we still usually use Q and P, where whatever the demand or supply piece of it would be the Q. So here I'd say that Q equals F of P, because demand is a function of price. So since it's a function of price, that means our P values are acting as our X's. So the points that we're going to want to work with are P, Q's. So now I can go back and I can pull out this information that we're given. So we're told 50 tickets at $10 and 75 tickets at $8. So that's essentially getting us the 2 points that we're going to need to be able to write this equation. So we've got a price of 10 for a quantity of 50 and a price of 8 for a quantity of 75. So I pull those two pieces of information out. I have my 2 points that I can now write the equation of a line for. What's the first step in writing the equation of a linear line? You need the slope. So we've got to find the slope first. So 75 minus 50, 8 minus 10, 25 over -2. Sorry, these are bothering me. And that reduces to -12.5. So that's our slope, and now we've got to actually write it in terms of, our y equals mx plus b, which in this case would therefore be q equals mp plus b. I keep forgetting which class I've said this to, so I'm going to say it even if I've said it already. If you prefer to work with x's and y's, you can. The only thing you need to be careful of is at the very end of the problem when you write your final answer, it has to be in terms of the variables given. And I know we weren't given P and Q, but with demand and supply and cost, revenue, and profit, those are the variables that we use. We use P and Q. So if you were to work with X and Y, that would be fine for all your, scratch work and figuring out the slopes and the B value and all that jazz. But then when you actually write the answer, it should be in terms of the correct variables, especially for Wiley. Wiley is very, very picky about variable names. If you have everything correct, but you have an X instead of a P, it's going to mark it wrong. So just be aware of that. But if you like working in terms of X and Y and it's easier for you, you can. But anyway, so now I got to pick which one of these two points makes me happier. The 1050 makes me happier, so I'm going to use that to find my B value. So my Q value is 50, M is negative 12.5, P is 10, don't know what B is. So we've got 50 equals negative 125 plus B. Add 125 to both sides. B is 175. And so our equation is Q equals negative 12.5 P plus 175. So that's our demand equation. But we're not done because there's still another piece of the problem that we haven't finished yet. And that's when we're asked to find the revenue function. So reminder, revenue equals price times quantity. When I said you're going to want to remember that, I meant it. So revenue is price times quantity. There's a Q right here. There's a Q right here. And I just found what Q is equal to. What we're going to do is we're going to take that demand equation and plug it into Q for the revenue. So we're going to have revenue equals price times negative 12.5 P plus 175. Technically, you should distribute that P value to get negative 12.5 P squared plus 175 P. And so in this case, I just wrote R, which would be perfectly fine, but it's technically R of P now because of the fact that we were left with P values, which is why I left it off to begin with. I was being slightly strategic because I knew that, usually we write R of Q, but in this case, it actually turns out to be R of P. I think I mentioned that before where like 90% of the time it's R of Q, but sometimes it's R of P. This is one of those times. Questions? All right. Okay. Last piece of 1.4 is the equilibrium point. The equilibrium point is where supply and demand are equal. So it's kind of like the break-even point, but for supply and demand instead of cost, revenue, and profit. And just like the break-even point, this is also made up of the equilibrium price and equilibrium quantity. And just like with break even, Wiley can get a little back and forth about whether they want one or both. I always want both. So say I wanted to find the equilibrium point if our demand equation is 100 minus 2p and our supply is 3p minus 50. Well, the equilibrium point is when demand equals supply, so we just set those two equations equal to each other. So I've got 100 minus 2p equals 3p minus 50. I personally like to get the variables together first, and I like my variables to be positive if they can be, so I would personally add 2p to both sides first. and then add 50 to both sides. And then divide both sides by 5 to get 30. So that's my my equilibrium price. So now I need to find my equilibrium quantity. And again, the demand and supply values are both quantities. And since they're equal at this point, it doesn't matter which one I use to find the value. So it's whichever one makes me happier. So I'm going to use the demand. So I'm going to take that p-value of 30 that I just found, plug it into either supply or demand. I'm going to get 40. So just to be clear, I might say $30, 40 items. Just to be clear that those are my two pieces. Apparently I can't box this. Where'd my 0 go? There we go. Savvy? Questions about 1-4? We're gonna start 1-5 in a second if there are no questions. All right. We're gonna start 1-5. I'm gonna talk about your homework at the very end of class. I'm gonna stop a couple minutes early to ramble about a couple of things. But I will talk about that at the end because your homework as it stands right now includes 1-5. But again, I'll talk about that later. So I'm gonna unshare this and now share the new 1.5. All right, 1.5 is exponential functions. So up to this point in time, we've only worked with linear functions, so now we're finally going to get a function that's not linear. So, and let's see, we end at 2, so okay. So let's say I've got this table here. It's considering years and a population in millions. The first thing I want to do is let me look at whether or not this might be linear. So, you know, each of these years go up by 1. So since they go up by 1 in each case, to find the slope, I would literally just need to worry about the change in population, which is why I have this column here. So let's look at these change in population. So this one's just nothing because there's nothing to compare it to. But so this line is essentially going to say the difference between these two. So the difference between those two populations, 14.66 minus 14.235, would give you 0.425. And then if I find the difference in the next set of populations, I get 0.438. And the next set, 0.441. And let me just finish it out. 0.464, 0.478, and 0.492. I did change these values, right? Yeah, I did. Okay, cool. So obviously, that very rightmost column that I just filled out, they're not all the same number, obviously. So this can't be linear data because all of these years go up by 1, so we would need these change in populations to be the same to have constant slope. So this is obviously not linear data. But consider the ratio between consecutive years. So I'm going to be very careful and I'm going to specifically choose consecutive years. So let me look at, 2007 to 2008. So in 2008, I have 14.660. And what if I divide that by the earlier population of 14.235? Well, if I were to do that, I would get this long obnoxious number, 1.029855989. And now let me try it for the next set of consecutive years. So what if I tried it from 2008 to 2009? Well, in 2009, I have 15.098. And what about dividing by the earlier year? This is going to give me 1.029877217. And I know there's an awkward space, but it actually kind of helps for what I'm about to do in a second. And let me take one more set, 2009 to 2010. So in 2010, we have 15.549, and in the earlier year, we have 15.098. Well, if I find that ratio, I'm going to have 1.029871506. So I know there's a really long, obnoxious decimals. Now, notice up to a point here, those are the same decimal. You know, so after 4 decimal places, they start to differ, but up to those first 4 decimal places, they're the same. And that's what we're going to focus on. We're just going to focus on those first 4 decimal places. So this matches up to 4 decimal places. And we're going to assume kind of the rest of it that doesn't match might be a rounding thing. You know, these might be rounded populations. So we're going to take, you know, the fact that they match up to 4 decimal places is a very good match. It's not saying that they don't match at all. They match very nicely. Up to 4 decimal places is pretty decent. So since these match up to 4 decimal places, we're going to say that looks pretty constant, that ratio. So we're going to say that this data has a constant factor. And so this is kind of the thing that makes exponential equations, is that instead of a constant slope, we kind of have this constant factor idea going on, where the ratio of these values are going to be the same. And so we can even, so in this piece right here, I specifically took populations from consecutive years. What if I didn't have consecutive years, but I still wanted to figure out if this data was exponential and had a constant factor? We're still going to be able to do that. So say, can you find this factor without using consecutive years? The answer is yes. It just gets a tad bit gross, if I'm honest. But here's how you would do it. You would calculate the change in whatever your x value is. So take the 2 values that you're looking at. They don't have to be consecutive. This works for consecutive. It's just that change of x would be 1. But whatever your change in x values is, it's going to be listed as change in x. And then what you're going to do is you're going to find the change in x root of the ratio of the 2 y values. Told you it gets a little gross. Which can also be written like this. What I mean by this piece here, so for a calculator, most graphing calculators have a, nth root button, but they're harder to find. So a lot of times I want to say like the 4th root of 16. You can write that in as 16 to the 1/4 power instead, and it's the same exact thing. So, whichever format floats your boat. But that's how you'd be able to find this factor even if you don't have consecutive numbers. So for example, let's say we looked at 2007 to 2009 in the above example. Can I get to that? You know what? Let's get numbers that we can actually see on this screen. So 2009 to 2011, let's say. And I need to grab my calculator because I have the wrong ones in my notes. Sorry. So if we wanted to go from 2009 to 2011, whoops, that's gross. Change in x would be 2011 minus 2009. I would suggest putting the larger x value first and making the one with the larger x value the x2. It works no matter which way you go, but when you have a negative root, it just makes things grosser. So if you can have the root being positive, it's better for everyone's life. So that would be 2. So now the y values associated with that, so essentially the ratio we're going to be looking at is, so the population in 2011, so 16.013, and then the population in 2009, so 15.098, and then we're going to take the second root. Now technically, maybe I should have chosen 2012. You don't need to write the little 2 there because it's just the square root. If that's any number besides 2, you need to write it in there. But the second root is just literally the square root, so you don't have to put the number there. What up, Jake?
I'm sorry, you could have possibly said this already, but where did you get the 16 and the 4 from for the equation? I know. I don't know.
The 6. Oh, over
Like, for the
here?
calculator part. Yeah.
I just made those up.
Oh, so yeah. All
It
right,
was
my
just
bad.
to demonstrate how you can type it into a calculator.
Okay.
Yeah, sorry, that's
Gotcha,
fine. Maybe I should
gotcha.
say
All good.
for example. Sorry. So if I take the square root of this, so I take the square root of 16.013 divided by 15.098, this becomes 1.0298, blah, blah, blah. But up to the 4th decimal place, it's exactly what we were expecting it to be. Just to hit it home one more time, say I wanted to go from 2008 to 2012. Well, that's it once it catches up to me. Come on, there we go. Well, that's a change of 4. So we'd be taking the 4th root of the population in 2012 was 16.491. And then 2008, 14.660. And that would give you the same decimal. I'm just trying to show another way with a different root. So again, kind of gross, but can be done. So if you have consecutive numbers, it's like much nicer for our lives if they already have consecutive numbers. But if they don't have consecutive numbers, we can still find the common factor if it has one. We just have to do a tiny bit more work. Hopefully that makes sense. So I'm going to go through this first set of definitions, and then I'm going to call it. I've got to talk about a couple things generically. So let's just fill out this first few set of definitions, and then, yeah, we'll be done. So we say that P is an exponential function.
Sorry, could you scroll up for like a half second?
Yeah.
Hmm.
Leave it here for a little bit. So P is a exponential function
Ooh,
of T. Let me scroll up a little. There we go. So it's an exponential function of T with base A. If we can write it as P equals P naught A to the T. So P naught here is going to be called the initial condition. Which is when T is going to be equal to 0. And A, well, A is called the base. It is going to represent the factor P changes by as T increases by 1. So essentially, in the hoopla we just were looking at, our A value would be that 1.0298, that common ratio between the values. And then a couple of things. If A is greater than 1, we're going to say it's exponential growth. If A is between 0 and 1, it's going to be exponential decay. While they do exist, not really, but they do exist. We're not going to deal with negative A values But one thing I should really stress that I always forget to stress. For an exponential function, a is never equal to 1. So say you were trying to find whether or not a set of data was exponential and you were getting that the common factor was 1, then it's actually a linear function. This would be actually linear. So an exponential function has to have this format, and a cannot be 1. Also, a is equal to 1 plus r. This is a big one. Yep, this gets to be a lot. So a equals 1 plus r, where r is the decimal representation of a percent change. If r is greater than 0, we have growth. And so these two things are the exact same thing. If r is greater than 0, then a is greater than 1. And similarly, these two mean the same thing. So if r is less than 0, it's decay. I know this is a lot of definitions at once. And the last piece is that the most common base is the number e. So just like pi is a number, e is a number, 2.71828, blah, 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 blah. Technically continues on forever. I should have put some dots after that. This is going to be called the natural base. And your calculator does have an E button on it. It depends where, depending on what calculator you have, but I'll try to put up some information about where that is. Because usually I would show it to you in class on the document camera, but it doesn't exist here. So I know that's a lot of information for this set of functions. It does get much more maybe not in depth, but there's a lot more going on here than with linear functions. We are going to stop here. You're going to be looking into 1.5 more on Monday. And so now I have to talk about a couple things. But before I do that, does anyone have any questions about what we just ran through with this?
Yeah, I have one question. What was the title of this section again?
Yep, it's exponential functions.
Exponential functions.
Yep.
Thank you both.
I'll just scroll back down here in case
You're
anyone needs
welcome.
it. Anybody else? Good ones. Device. All right, a couple things then. Your homework was technically on 1.4 and 1.5. And while yes, we did barely talk about 1.5, we haven't actually really gotten into any examples or anything like that. And plus my other two classes didn't even get this far. So what I've decided to do is for this week's homework, it's only going to be counted on 1.4 material. And now, unfortunately, I can't go back and just delete all the questions from 1.5 off of the homework without making everything explode. So, and I'm going to send out, there's going to be an announcement on Blackboard with an email so that it's all in words so that you can refer back to it later if you forget what I said. But essentially, I'm only going to count this homework based off of the points for the 1.4 material. And you should be able to figure out which ones are 1.4 and which ones are 1.5. When you're doing the questions, there should be like a little sidebar, and it should say like section 1.4 question 005, and give you a list of those. Just don't touch the ones that say 1.5. So say, I don't remember the actual numbers, but say the entire thing was worth 96 points, but there was only 50 points that were for 1.4, then I'd only be scoring it out of 50 points, okay? Now, again, since I can't change it in Wiley after the fact, your grade on Wiley is gonna look quote unquote bad, but the grade that I take into my actual calculation and the grade that I will post on Blackboard, because I do eventually get those grades posted in Blackboard, will just be based off of the 1.4 material. You will eventually need to do the 1.5 material, but it will appear on the next week's homework. So it's still going to come up. You're still going to have to do the questions, but just don't touch them on this one. They'll show up on next week's. And again, I will send out that in an email so you can refer back to it later. The other thing, Monday, since it's Labor Day, And usually for a normal semester, that would mean that we don't have class at all. But since they rearranged the schedule, and you might already know this from your other classes, but just in case you don't know, it's an asynchronous day. Okay, so that means that we don't officially meet. That means that I have to post some lecture videos and you get to watch them in your own time. Now, I need to make sure that I'm allowed to do this next thing I'm about to say without the university getting mad at me. I assume I can, but I'm just going to double check. And I will also send out information on this as well later. I am planning on probably still being here for anyone who wants to see me walk through the material in, quote unquote live, but you don't have to be here. It's an asynchronous day. Technically, what you're required is that you need to watch the lecture videos that I post so that you're caught up on material. We do cover material on Monday. It's just that we don't officially meet, but most likely, as long as I'm allowed to, I'm still most likely going to be here and going over it live, if you will, for anyone who would rather view it that way. But again, I will send out information on that once I get the go ahead on that later. I think that's everything I had to say about that. So again, both of those things, the official information